Are you able to share the screen?
Yes, let me do it. Yes.
No, it's okay. You can start.
Thank you very much. So I'm sorry I came in a minute later. Let's get to restart my computer. So here is the title of my talk. It is about invariant theory for reductive subgroups of reductive groups. It is a topic that I have been thinking on for a long time, and I'm happy to present it now in this seminar in the Institute. It is my first seminar since I started working in the Institute in the beginning of this year, and I'm very grateful to all the colleagues for the friendly atmosphere and interesting seminars. About the topic, there will also be another seminar on Tuesday, and I was asked whether it would be on the same topic, and it will not be exactly the same, but there will be some overlap. But my research has two sides, one rather geometric and one more algebraic and combinatorial. And today I'll talk about more in a more classical setting, invariant theory, and talk about rings of generators of rings of invariants. And on Tuesday there'll be a more geometric talk. So with all of this, let me just phrase a very simple question. If we have a group and a subgroup, we can ask which irreducible modules of the larger group admit invariant vectors with respect to the subgroup. This is a very basic question, almost no assumptions. But well, underneath are the assumptions that I will have here. So I take reductive complexly groups. Connected is also an assumption. So all such groups are linear algebraic. So we can think of them as finite, not finite, but closed subgroups of GLN for some large enough n. And reductive means that all their representations split as sums of irreducibles. And so, but above we are taking an irreducible representation of the large group and asking for invariants with respect to the subgroup. Now, this topic, or more generally decomposing the G modules under G tilde, occurs in many situations. For instance, if we have a group action on the manifold and then we take a point and we take the stabilizer subgroup of this point, it's a subgroup. And we can ask about fixed points of this subgroup in some representations of the larger acting group. Or many canonical objects are defined as invariant vectors with respect to a suitable subgroup. Say the determinant or a trace. So this general question has many faces and it occurs in many situations, but I will try to treat it here structurally. So let me introduce the main language which will be spoken throughout this talk. It will be the language of structure theory of semi-simple and reductive Lie groups. So we fix the maximal torus inside our G. And maximal torus, this is the multiplicative group of C to the power R. And a maximal solvable subgroup, think upper triangular, the example will be below. And then lambda will be the character or weight lattice in this part of the theory. It's usually called weight lattice. So this is the character lattice of this torus, which is a free abelian group of rank R, so a lattice. Now, the representations of G, if we take any representation, it splits under T. T is an abelian connected group of semi-simple elements, because C star we take. And then any representation splits as sum of weight spaces or common eigenspaces for all elements of T. And the respective eigenvalues are actually elements of big lambda. And we call the support of V these lambdas that actually occur. An important example of support is if we take the reducible representation of G, then and decompose it under T, then the Lie algebra of T itself, T being abelian, the diagonal, is the zero weight space, it commutes under the adjoint action, and then the other weights are called the roots of the Lie algebra. So the non-zero weights of the adjoint representation. And we can partition them. This is a finite set. We can just pick a hyperplane not intersecting any of them. Everything that's on one side will be called positive roots. And if the maximal solvable subgroup above is chosen suitably, then this will be its support without the zero. And then if we take the negatives, we'll still be in our set. So delta has a decomposition, delta plus and delta minus. You can think of an example below. These are this is GLN where T is diagonal and B upper triangular. And the character lattice is generated by these epsilons, epsilon j, just pulling out the jth coordinate. And the roots are the differences. The root spaces are just the one-dimensional spaces generated by the unit matrices, where we have only one at ijth place and zeros elsewhere. And so B will be the upper triangular, B minus will be the lower triangulars, and they have the corresponding roots. Here I have delta plus, which is epsilon I minus epsilon j with so ordered indices. In the opposite order, we'll be getting delta minus, and obviously minus delta plus is equal to delta minus. So these are the root space decompositions, and here I have this set of dominant weights. So we distinguish those which pair under the Killing form or suitably defined orthogonal product on the weight lattice. So So those that pair non-negatively with the positive roots will be called dominant weights, and they form a simplicial semigroup. So the generators of these semigroup are called fundamental weights. So for GLN, the example, these would be sums of the epsilons with ordered entries. There is an obvious action of the symmetric group. So this is somewhat standard notation for Lie theory. If this is not your cup of tea, then bear in mind that we have a simplicial semigroup, lambda plus. And there is a theorem of Cartan-Weil, which tells us that the irreducible representations of G are parameterized by this simplicial semigroup, lambda plus, the set of dominant weights. So above it is written that actually the characters of T also define characters of B, because B modulo its commutator is isomorphic to T. So we have a chance of having B eigenvectors, and every irreducible representation has exactly one. And its weight determines the representation up to isomorphism. And so for lambda dominant, we write this for a model of an irreducible representation with this highest weight. And there is an important fact that the tensor product of two irreducible representations, it decomposes somehow. And there is one special component that we always encounter, and this is the one with the sum of the highest weights. So this is a semigroup again, and this is for us an important problem. So why am I stating this theorem? Well, we want to know, our question was about the irreducible representations of G and which of them do have invariants for the subgroup. And here is a set parameterizing the irreducible representation. So now we can write our question more concretely. Now, if we have an embedding, we can consider those dominant weights so that the corresponding irreducible G modules have G tilde invariants. And here is a slightly different question in a slightly different set. Those lambdas, which when you multiply them by some natural number, then you acquire invariance with respect to the sum. So we have a semigroup, so this multiplication is fine. And we can ask this question. So the above is a generalization of the Littlewood-Richadson semigroup. This has the LR. And the 0 is because it is not exactly the Littlewood-Richadson semigroup. It will come on the next slide. And below the A of iota, this would be called the G tilde ample cone in some other context, hence the I. But let's, so this will be explained further on the notation, but we can consider this set. So the irreducible representations which have invariants, they are parameterized by this set LR0. And the other one is, well, somewhat similar. How similar? So they're both semigroups. And furthermore, one of them, if we, so this CLR0 is the generalized Littlewood-Richadson cone, the convex hull of those, of the ones having invariance. So I take convex hull in the real span of the lattice. And then if I have this cone and intersect it back with the lattice, I get some integral points. And so I'm getting all the integral points. So what does this mean? If we can, if an integral lambda is inside this cone, then some multiple of it actually does have invariant. So this is part of a result. It's somewhat of a folklore result attributed to Brion and Knop and published first by Elashvili. So it says basically that these are finitely generated semigroups, the two above. And because of this finite generation, and so every lambda can be put from A into LR, because we have finite generation, then we can pick one which works for all. And the minimal such will be called the saturation coefficient. So this is a matter of saturation for some cone, a lattice cone, rational polyhedral convex cone called the generalized Littlewood-Richadson. So here is a property. I'm going to call it property A because of this notation A above. So if all highest weights have invariants up to being multiplied by a suitable Q, then we say that we have the property A. So this means that the subgroup has a lot of invariants in the G module. How often does this happen? So before going there, let me actually give an example here at the end of this slide where it doesn't happen. So more generally than just taking invariants, we can consider the branching loss or restriction of representation along our embedding iota. This means I take an irreducible representation of the large group and split it as sums of irreducible. So everything wearing a tilde is an attribute of the subgroup. And then we have some multiplicities, which is what? Well, the homomorphisms from the supposed subrepresentation in here. This may be 0 or maybe non-zero. But in any case, this homomorphism space can be written. So the linear, just the linear maps are what's in the bracket without the upper subscript here. So the tensor product of the domain dualized with the target space, standard linear algebra. Oh, there is a dimension missing here for the tensor product. But so the fact that we require G tilde homomorphisms means that we take invariants in the tensor product with respect to this embedding seen here below. So the tensor product is a module over the product group, G tilde times G, which contains the G tilde diagonally embedded here with the identity and here with the foregiven iota. And this is how G tilde acts on such tensor product. And we can ask for invariance. And there is a dimension here, because we care about the multiplicity as a number, how many times this occurs. So the Littlewood-Richadson semigroup without a zero, this is the more classical one, and the classical one will come right away. So these are pairs of highest weights, so that this is non-zero. Again, a typo, I'm sorry. This should be that this space is non-zero. There should be. But now that I'm acting here and I have this product group, this product of Weyl chambers is just the Weyl chamber of the product group. So this is LR0 from this new embedding that we obtained from delta. So every generalized Littlewood-Richadson cone or semigroup is one of these LR0, but for another iota, the one obtained by multiplying iota with the identity. Here is an more concrete example. So if the large group G is just a product of the small group with itself k-fold. So the dominant chamber is a product of the small dominant set of dominant weights k-fold with itself. And when an irreducible representation of the large group is just a tensor product, k-fold tensor product of irreducible representations of the diagonally embedded. And then we have tensor product decompositions. And their multiplicities are known as Littlewood-Richadson coefficients, famous numbers occurring in Schubert calculus and elsewhere. So this is perhaps the most classical branching problem. And according to the above, we see that the branching problem for a k-fold product is the problem of invariance for a k+1 fold product. If I add one more here and ask for invariance, then I would be looking at such just adding one more tensorand and asking for invariance. And according to the above, this would compute the multiplicity. So this LR, it can never equal the product of the two Weyl chambers. Sorry, I have not written it on the slide, but the property I never holds for the identity times something. In other words, if the large group has a component isomorphic to the subgroup, to which the subgroup projects surjectively, then we can never have invariance everywhere. Why? Well, just by taking lambda, the large weight equals 0, and the small weight non-trivial, we'll be asking for G invariance in an irreducible representation of G tilde. So this factor will be trivial, but this remains irreducible, so it couldn't possibly be invariant. So we find, if we are looking at pairs, we can find pairs without invariance. This means property A doesn't hold for this product morphism. The saturation problem here has been attacked and very famous actually for diagonal embeddings. This was Horn's conjecture proven by Knutson and Tao in the end of the 90s. Also works by Woodward, contributions by Klyachko, and the playad of other mathematicians. Hermann Weyl, of course, has fundamental contributions, Horn himself. This problem, the tensor product decomposition problem for GLN, is also related to sums of eigenvalues of Hermitian matrices. So, Hermitian matrices, sums of Hermitian matrices, and how do the eigenvalues of the sum depend on the eigenvalues of the summand, or a k-fold sum? So Hermitian matrices, because the unitary group is a maximal compact subgroup of GLN here. And this can be interpreted in this fashion. And they say that the saturation coefficient is equal to 1 for the diagonal embedding of GLN. So if we have invariance in some multiple of lambda, then we have invariance already in lambda. So this is remarkable property of Littlewood-Richadson coefficients for GLN, that if the coefficient doesn't vanish for when all the weights are factored with the same factor, then or multiplied with the same factor, then the original coefficient also doesn't vanish. Remark, this saturation problem, or the computation of the saturation coefficient, is widely open in general. It is one to my knowledge, of the most widely open problems in representation theory. Even for diagonal embeddings beyond GLN, not everything is known. There are hypotheses, unproven hypotheses for simply laced linking diagrams. So even for simple groups and diagonal embeddings, not everything is known for the saturation coefficient. And the methods that have been employed so far have always been special for special embeddings like the diagonal of GLN. And the method of Knutson and Tao doesn't even generalize to the diagonal embeddings of SO, for instance, or SP. And well, further methods have been found and refined, but they're still handling separate cases and even diagonal embeddings. So we'll see something more about the saturation problem later on with some simple case that we have worked on. So the prototypical case, besides the diagonal embeddings in these branching laws, let's go back to the invariants and really see the prototypical situation for invariants. This is just that if we have a representation, so the large group is just GLN, and V is CN, it's natural representation, which is irreducible under GLN, so it's one of those V lambdas. And the coordinate ring, polynomial ring in n variables, has homogeneous components which are irreducible under GLN, the symmetric powers of the natural representation. And they actually have highest weights which are multiples. So these multiples of the dominant weights, they are not random at all, they are linked exactly like this. So the representations whose highest weights are the multiples of lambda do form a ring, like this one here. So this is just the polynomial ring, and then we are asking for G tilde invariants. So the subscript denotes homogeneous polynomials of degree 2. And of course, we have to dualize the symmetric power if we want to go to polynomials, actually. But a representation has invariance if and only if its dual has. So actually, this set LR0 is stable under dualization. So on G level, the dual of an irreducible is irreducible, and for the subgroup, there are invariants in a representation if and only if the dual has invariance. But what may happen is that there are no invariants or no non-constant invariants because the constant is always there. So if I say no invariants, this means no non-trivial ones. And here are a couple of examples. The symplectic group inside here, this is very large. It acts transitively on the set of non-zero vectors in its natural representation, and there is no chance for invariance. Spin 10 in the spin representation, which is 16-dimensional, also has no invariance. Higher spins do have invariance. Lower spins do have invariance. Well, except spin 2. And here is another one, odd dimensional SL, odd dimensional SL in its second fundamental representation, so the two vectors. This lambda is an exterior power, not the lattice. And actually, Katz has classified all irreducible representations with polynomial rings of invariance, in particular with trivial rings. And the classification is not huge, but well, I have not listed it here. But there is a tangible classification. There are a few more representations. And this exhausts everything where there are no invariants. And this would be the case where property A also does not hold even for the LR0, not only for LR. Let me just recall Hilbert's theorem, mostly for the second statement. So the finite generation is famous of the ring of invariants in a polynomial ring, and also the ring of an algebraic G tilde variety. It is finitely generated by homogeneous elements, and the common zero locus of the non-constant generators, or similarly, the common zero locus of all elements which vanish at zero, so constant, zero constant term. So this common zero locus is called the null cone and is an algebraic variety with so the zero locus of the invariance of positive degree. It will be denoted in this way when I want to make sign of the representation and the subgroup with respect to which I take invariance. And Hilbert tells us that this actually consists of all vectors which are pulled to zero by G tilde. Of course, in the closure of the orbit, because if the vector is non-zero, there is no chance its orbit will meet zero, but in the closure it can. So this is everything that's dragged to zero. And here below, we actually have a stronger statement. We can actually drag the vector to zero by a one parameter subgroup. So we have a homomorphism from C star lying in here, and in particular in GL of the representation. And so this is a one parameter C star family of linear operators, and we drag the vector to zero by it. This is also called the unstable locus or null cone. If V is the Lie algebra of G tilde, then these are exactly the nilpotent elements. Hence the name null cone, or because they all sort of get together at zero. So this is somewhat natural because the homogeneous elements all vanish at zero. In particular, so do the homogeneous invariants. And then the invariants cannot distinguish between the orbits. They must take the same values at all orbits adhering to zero. This is why this space is usually excluded when we take GIT portions, but more of that another time. Now, I should say that this paper of Hilbert, where this is proven, is one of the most remarkable papers of all time, from 1883 and up to 93. There is a couple of more, but even in the first one, he proves that ideals are in a polynomial ring are finitely generated, and non-trivial ideals have non-trivial zero loci, and he deduces that this ring is finitely generated. And this is the article where a big part of the fundamentals of algebraic geometry is introduced in one go with this goal to compute the invariance, to show finite generation. So this null cone is important, and we can formulate a simple criterion that there will be no non-trivial invariants if and only if the null cone is everything. So everything gets pulled to zero, or its codimension is zero, which is a trivial statement as long as it is a subvariety, and it is because it's the vanishing locus of a finite. So this is one criterion that we have, and now we should generalize this not to the case of GLN and its natural representation, where we're looking at polynomial ring and the invariants therein, but to more general G and lambda. So if we take, it is more suitable to work projectively. So we take the projective space of the irreducible representation of the large group, and then we take, this is the large group acting on the highest weight vector. So this would be the vector fixed by the Borel subgroup, projectively fixed and otherwise acted upon by this character. And I denote this by X lambda. This is called a flag variety. This class of varieties is very important, special in one sense, but also very universal. So all homogeneous projective varieties have this form: a semi-simple group and then the orbit of a highest weight vector. And their classification is practically equivalent to the classification of semi-simple groups. And fundamental examples are the Grassmannians, and they carry the name flag varieties because the flag varieties for G equal GLN consist indeed of flags of subspaces. So a one-dimensional into a two-dimensional into a three-dimensional. We make the complete flag variety. We make every step. And this is a projective variety as it obviously embeds into a product of Grassmannians, because the one-dimensional space is an element of the projective space, and the two-dimensional space is in the two Grassmannian. And then if we have the flag condition that the spaces are nested one into the other, then this is an incidence relation on the product of Grassmannians. And since the Grassmannians are projective by the Plucker embeddings, all of these X lambdas, all of these flag varieties are projective. So for the other classical groups, we have to take chains of isotropic subspaces. And for exceptionals, it's a bit more complicated. But again, there are concrete geometric models for those, as well as this universal representation as orbits. So the stabilizer is a parabolic subgroup. This means a subgroup containing B because we have a highest weight vector. And then this G mod B, the complete flag variety, surjects, obviously. So there is this one master variety which maps onto all of them. And actually, we can pull back the O of one, the antitautological line bundle on the projective space here, and those bundles will generate the Picard group. But again, I'm just going to stick to coordinate rings here, and this line bundle story, in what the Borel-Weil in this form tells us is that the coordinate ring of this space. So in degree 1, we clearly have just the dual of B lambda. And then in higher degrees, we have the multiples, just as we had for the polynomial ring. But now these are smaller spaces. We don't have the entire symmetric powers. but we have some quotient of these symmetric powers. And it is irreducible in every degree. So what is the point here? The coordinate ring of X is irreducible in every degree. And, well, these are the highest. Now, this is very well suited for our problem with the semigroup having invariants. Here is a remark that actually, because the parabolic subgroup that depends on lambda only up to a multiple, actually the variety is the same. It is embedded in a different space, but the variety as a coset space, G modulo the stabilizer, is the same. And so is the null cone inside it, where the null cone is defined as the zero locus of the invariant ring over here, of course, of positive degree. And it is, again, by Hilbert's theorem, equal to those points in the variety, which, written as vectors or projectivizations of vectors, can be dragged to zero by our acting group, G tilde. So now our G tilde ample cone for the embedding, A of iota, the lambdas whose multiples contain invariants. Well, now these multiples are all written into a ring, and we can just say, well, this ring, oh, I beg your pardon, there should be a G tilde here, so there should be invariants, otherwise the ring is always non-zero. So where the mouse is now, there should be G tilde invariants. Or in other words, the null cone must have positive codimension. So we must have non-trivial elements. Now we have rewritten our A as well in terms of rings. So now we are handling invariants in rings, which is better than just individual irreducible modules, because we have Hilbert's theorem. And because we have this geometric counterpart of the invariant ring, the null cone. So here is a number that sticks out, just the codimension of the null cone, which depends on lambda, so that we are taking this irreducible representation in the orbit of the highest weight vector, and on G tilde, the subgroup which is acting and by which we are looking at invariants, and by which we have a null cone. So this number seems to be important here, because just the positivity of it means that we have our G tilde ample situation. The terminology ample comes from the line bundles having sections. Now, we can also define this more general cone on the bottom, AK. So this cone is just defined by this codimension being larger or equal to K for K greater or equal to 1. So the above is A1. A of iota is A1 of iota, but then we can go further than 1. And these are also cones, or intersections of the lattice with rational polyhedral cones, as one can show, and as I will indicate in what follows. So let's focus on this null cone in X lambda, and we want to know about its dimension and codimension. So the dimension of X lambda is known because of this surjective map from G modulo B. The dimension of G modulo B is the number of elements in delta plus. So this is a simple combinatorial invariant of G. And the dimension of X lambda is, well, some roots inside delta plus, which are also easy to compute and well known. So the core part is not much of an issue, but we have to compute the dimension. It is suitable to assume that we have tori in the subgroup and in the group which are nested. And then, so the null cone of this X for a fixed lambda now, with respect to G tilde, as I said before by Hilbert's theorem, these are the null cones for the individual gammas, one parameter subgroups of G tilde, where these were the points which gamma drags to 0 when its parameter goes to 0. So positive weight vectors for gamma. Right? We have a positive weight vector, then it will be pulled to 0. So now every one parameter subgroup of G tilde is conjugate to a one parameter subgroup of a maximal torus by the standard conjugacy theorems for tori in reductive groups. And hence, the null cone with respect to G is equal to G times the null cone with respect to T tilde. But then since T tilde is inside T, I can include this in here, in the null cone of X with respect to T. What is the purpose? Why would I substitute and have this imprecision here? Well, because now this part is independent of G tilde. And perhaps if I can measure this part and see how G tilde will act on it, I can get my hands on some dimension, codimension, or further structure. Now, let us focus on this variety for a moment. The null cone for just a one parameter subgroup, and bear in mind this is directed one parameter subgroup, so I'm pulling the parameter to 0. I'm not pushing it to infinity. To push it to infinity, I would have to take the inverse one parameter subgroup, which is always there. But for the formalism here, it is best to distinguish between gamma and gamma inverse, although they have the same image inside G, but it's a different parametrization. So this variety, so the points pulled to 0, is preserved by the parabolic subgroups defined by gamma, actually in either in G or in G tilde. So this gamma lands in G tilde, so this subgroup will be well defined. One parameter subgroups are much like the weights, so the subgroup is defined in a similar fashion, actually. For all intents and purposes, you can think of gamma as also being a weight. Using the killing form. So these parabolic subgroups are defined similarly to the ones I described as stabilizers of highest weight vectors. But my point here is that actually both parabolic subgroups, also the parabolic subgroup of the large group, acts in here. Why? Well, a one parameter subgroup of G tilde by composition is also a one parameter subgroup of G. And the set being pulled to 0 doesn't refer further to the tildes. X is defined just by G, the large group. So it's parabolic subgroups that should act on this space. I'll come back to this in a moment, but for now, let me use the P tilde action and note the following. So since we have this action, we have a surjective map first from this product. If I act by P tilde on the right here on the group, I act on the right by the inverse, and I act on the left on this set, which is stable under P. And so the quotient by this left-right action is a fiber bundle, denoted in this way, which is a fiber bundle over this flag variety of G tilde of the small group. Because if I just act on the group on the right by P tilde, well, I get a flag variety. And I have then a surjective morphism from the complete flag variety of the subgroup. And furthermore, this product now maps just by multiplying, by acting by G tilde on the elements. This belongs to our variety that everybody acts on. And so we can map it here, just all possible images, which refers to what we had above. And from this, we can deduce bounds because we have, for a fiber product, we have a bound, we have the dimension, it is just this sum below the fiber plus the dimension of the base. So this image, which is an image of this fiber product, should have smaller dimension. And now this sum here, I can further compute because of this surjective morphism and because the dimension of G tilde mod B tilde is just the number of the positive roots of the tilde. And then I have to just add this piece. Well, for this piece, I can add, as noted here above, I can just add the dimension of something larger. The entire null cone for the entire torus of G, I forget about G tilde. And why is this good again? Well, because this last summand, we are getting rid of the tildes and they're quite annoying in the notation, but if I try to pick letters for also all the elements of the subgroup, it will be difficult. So everybody uses a tilde. But the important thing is that this last element here is independent of G tilde, and I would denote this number called the codimension, just an abbreviation for the codimension with respect to T now of lambda. Now here there is nothing dependent on the subgroup. And I have isolated the subgroup as far as dimension is concerned, only in this numerical invariant which depends on nothing but the isomorphism class of the subgroup. Now, why wouldn't I be able here to immediately bound the dimension of the null cone of G tilde? Well, because I have such an inequality for every gamma, and to have a general bound, I have to know, for instance, that here finitely many gammas suffice. And finitely many gammas do suffice, as various theorems tell us. For instance, the stratification theorem of Kirwan-Ness for null cones of such actions. But here is a more concrete argument about it. And So I should finish in a few minutes, I suppose. So maybe this more concrete argument will not be given in details, but rather I would state this theorem that there is a finite set well defined by just the embedding, uniquely determined by iota, so that the null cone is this finite union, G tilde acting on the null cones of these few one-parameter subgroups, structurally defined. And for each of them, it's this null cone is a union of parabolic orbits. But now for the large group, large P, so without a tilde, because these sets are preserved, as I said before. And the W here is an element of the Weil group, normalizer of T, modulo T. And we'll be looking at those evaluating, so that W lambda evaluates positively on these prescribed finitely many subgroups, one-parameter subgroups, which are enough to stratify the null cone. And now we have this general bound that the codimension of the null cone, of this null cone here, is equal to the minimum of these codimensions, and then I have to subtract the positive roots as I had in the inequalities before. And then by just dominating these individual ones with L lambda was the codimension for T, the torus of our group G. And this L delta is defined here. So this is the minimum of all the L lambdas. And can be expressed in terms of lengths of Weil group elements. So how many simple reflections we need to turn one lambda outside of the cone of the positive roots. Now with these inequalities, we can imply that we can deduce a numerical invariant of the large group minus a numerical invariant of the subgroup here. And if this number is larger than a given k, then our property A holds, and even the codimensions of the null cones are always larger than k. So our property A here holds, and I have deduced the proper a criterion here which is independent of the embedding. It depends only on combinatorial invariance of the group and the subgroup. I didn't have time to give all the details, but maybe I'll talk some about those things, though in a slightly different context on Tuesday. But the important thing is these are combinatorial and independent of iota. And we have computed them for simple groups. And they are the following. So we could quickly observe that this varies with n. For the exceptionals, these are some constants. Except there is a problem for an. This invariant is equal to 1. And remember, I want it to be larger here than the number of positive roots of the subgroup. So it should be larger than 1 to do something useful. So this problem with the SLN, that it's equal to 1, is problematic. SLN is problematic, but it's the only one that's really problematic. And there is a partial remedy, which I will skip. So we can handle many subgroups of SLN. So there is a companion invariant. But here below we have a corollary that if the subgroup is SL2 or E8, then we always have the property A, as long as we have no diagonal factors, because as I said, when we have diagonal factors, then this property cannot hold. So E8 is quite a challenge computationally. SL2 is easier, but E8 is quite a challenge without this simple theorem. And there are some corollaries for classical groups. We have a simple criterion that the classical group SLN, SON, or SPN, if the n is larger than the dimension of the subgroup, and the subgroup is large enough, then the property holds. So for most subgroups of classical groups, because there are finitely many for which this inequality doesn't hold, for most subgroups of classical groups, the property does hold. So most subgroups have invariants in most modules. And just a last slide. As an application of this, we can now attack the saturation problem, at least for the invariants, if not for the branching rules in general. Because if all highest weights have invariants up to a multiple, then by defining the saturation coefficient of an individual weight like this, we are looking for the general saturation coefficient at the least common multiple, the minimal common multiple of the fundamental weights. And this can be computed for a torus, and a doctoral student of mine did compute it for SL2 subgroups, showing about 4 with many exact results, which I cannot state now, with one singular very odd exception, 12, for just this SP4 and its principal SL2 subgroup acting irreducibly on the 4-dimensional representation. The methods, I don't have time to outline, but why are SL2 subgroups important? Because if we combine them with tori, and we can do everything we want, from SL2 subgroups and tori, we can get all invariants. So these are some plans for further research on the saturation problem. So I am sorry for stepping a bit over time. Thank you very much for your attention. And this will be the end of my talk. Thank you.
Thank you very much for the talk. Do you have any comments or questions?
Excuse me, I couldn't.
You have, I can ask the people, not you.
Okay.
There's some questions or comments on the talk.
Excuse me, can I ask him 2 questions connecting with definitions? At first, what do you understand under the reductive group? This is first. And second, notation. What means G tilde? What G, this is reductive group, as I understand, but what means G tilde?
Right. So this is the first slide. So the G tilde is just, it doesn't have a meaning in relation to G. It's just I am using 2 groups from square 1. I have 2 groups. I will say what is reductive, but whatever reductive connected group is, the point is that they are of the same type. Rather than using different letters, because I also have to assign attributes to them, weight lattices and so on, I use tilde for the subgroup and G for the large group. Why is tilde the subgroup? Because the structure of the large group is more important, and the notation is more clear this way. But of course, the notation is a bit complicated. What is a reductive group? It has many characterizations. One of them is a compactification of a complexification, pardon me, of a compact group. And another one is a group over the complex numbers, all of whose finite dimensional representations are completely reducible. The link between the two comes from Weil's theorem that over a compact group, the representations, finite dimensional unitary, are completely reducible by taking orthogonal complement to subrepresentations and then making them unitary with the unitary trick, so integrating an arbitrary Hermitian form. And so a complex reductive group is a group which behaves very much like a compact group, especially as far as representations are concerned. So all finite dimensional are completely reducible, and the invariants between the invariants of the complex one are the same as those of the compact.
Thank you.
Some other questions? I cannot see in the moment, but getting the speaker once again for the very serious and very nice talk. And the next talk probably will be the next Friday at the same time. It should be by Vladimir Gerzhikov, real Hamiltonian forms and affine total field theories, special aspects.
Okay, so now that the official part of the meeting is over, I will transfer the hosting in the Zoom sense to the speaker so that you can continue with an informal discussion with him. This is typically done in a coffee room if the meeting is face-to-face. The speaker is the main object of interest and the host of that. So I think this is the natural thing to do. Okay.
Maybe
now we have no recorded chat